Welcome back, folks. I decided to leave this one in the rotation. Why not? It's fun. I'm leaving the nose off. Anyhow, more phasor analysis on circuits that have sinusoidal voltages and currents. So I'm just trying to get you comfortable with kind of the flow of how we work these problems. So let's look at a current divider. If we can do it with a voltage divider, we can also do it with a current divider. All right, so here we have what looks like a regular current divider that we would have seen earlier in the class, but we have a capacitor, and we have a current source that is defined as a function, okay? So we're going to follow that same path, kind of going up and around, right? We perform the phasor transform, okay? So let's look at we're looking for a complex number for each of our components. So we're going to get a phasor for the current supply. So this is going to be 400 milliamps. So I wanted a different color. 400 milliamps at an angle of -30 degrees. And the milliamps ends up here, right? That prefix modifies that magnitude. But that one's done. The complex number for the resistor, don't overthink it, is just the resistance. For the capacitor, again, go back and look at that table of impedances from a few videos ago, and we can see that Z sub C is equal to -J over omega C. So in this case, it's going to be -J over 1,000, right? I got the 1,000 from the coefficient of T there, times the capacitance, and that's 1 microfarad. Okay, a lot of folks forget, like, do this multiplication, then forget to invert it. Don't do that. Be better than me. A lot of folks, I meant, sometimes I do. But now I watch for it really carefully. Okay, so from that we get -J 1,000, so 1K. And that's again in ohms, it's an impedance. It's going to be in ohms. If you go through all of that calculus that I did a few videos ago and follow your units, you're going to see that it ends up being in ohms. Okay, so I have a complex number for each one of these components. And then we perform circuit analysis. Okay, so I say I out, except it's the phasor for I out, so it's capital I sub O. Okay, I out is equal to I in. Again, it's the phasor, so it's capital I. And we want to know the current through the capacitor, so we multiply by the opposite branch impedance now. Okay, so this is going to be R over R plus ZC. Okay, plugging in values for that, we get 400 at an angle of -30 milliamps. That prefix makes that unit really important, right? And we're going to multiply by 500 over 500 plus, no, not plus, minus J 1,000. Okay, minus J 1,000. Oh, you know what? I could have missed out on my chance to do an elevator joke there with my chair. Okay, so all we got to do is calculate that. So plug it in to whatever calculator you want to use and figure it out. So I'm going to do 500 over 500 minus J 1,000, and I'm going to multiply that by 400 milliamps at an angle of -30. Okay, and from that I get I out. So here's my phasor domain solution, 178.9 at an angle of 33. Come on. Oh, I broke it. Gosh darn it. 33.4 degrees, and that's in milliamps. So be really careful that you check the exponent, the exponent of the magnitude there. It's going to end up being in milliamps. Now, that's our phasor domain solution. We want to move back to the time domain. So we say I out as a function of t is 178.9 cosine. Omega, go back up, was 1,000. Right? If you forgot it, go look for it. 1,000 t, because the frequency doesn't change for these problems, plus 33.4 degrees. And all of that is in milliamps. Okay. And that's it. Not too bad. I think you can do it. So we'll do more in the live class. We're going to do some mesh. We're going to do some nodal. But look, all of the analysis is the same as long as you can move to the phasor domain and move back out of it. You already know how to do this. Okay, mesh analysis. I'm pretty sure that's what's coming up. So stay tuned and good luck.